right, in concept C, we are going to be working with some percent composition equations as well as some related calculations that we're going to be doing. This formula is on the back of your reference table. You're going to find that the percent composition by mass is mass of the part divided by mass of the whole times 100. You're going to see in our first two examples that the mass of the part is just the mass of a single element. The mass of the whole is going to be for the whole compound. So it goes back to how we calculate GFM. So in our first example, we're going to find the percent oxygen by mass of aluminum oxide. So we first have to write the formula for aluminum oxide. To find our mass of the whole, we need to know the GFM of aluminum oxide. So we have 2 aluminums, 3 oxygens, which finds a gram formula mass of 102.0 grams. The mass of my part is whatever element I'm looking for, which is oxygen, and I have 3 oxygens. So mass of my oxygen is just simply going to be 3 times its GFM, which is then giving me a total of 48.0 grams. Then at that point, once I have the mass of all the oxygen, the mass of the compound, I can then go into my percent composition calculation, filling in the values, again, of oxygen over the compound times 100, which gives me a mass percent of 47.1. All right, I would suggest trying this one out on your own and then checking back to see how you do. You should be finding the percent nitrogen by mass of aluminum nitrate. So the first thing you're going to do was write the formula correctly based on your oxidation numbers. Find the GFM of aluminum nitrate, which is 213.0 grams. Then we're interested in just the nitrogen, and I have 3 nitrogen present. So 3 times its GFM of 14 is 42.0 grams. Then going ahead to use the percent composition, putting the amount of nitrogen, 42.0, dividing it by the mass of the entire aluminum nitrate, and then arriving at a value of 19.7%, which is the percent composition of nitrogen by mass. So those are just some straightforward percent compositions using our compounds formulas. Now we can go one step further with this and basically use percent compositions given to us to find the empirical formula. And remember back from our Unit 6 that the empirical formula is when the elements of a formula are in the simplest whole number ratios. And this works for our molecular compounds. So, and some of our ionic compounds, which will always be in the simplest ratio. So we're going to use our percent compositions in order to determine empirical formulas. So for example, we could have a question like this where you're going to calculate the empirical formula of a substance that contains 50% sulfur and 50% oxygen by mass. So how do we go about doing this? The first thing we're going to do is we're going to assume that we have 100 grams of the entire substance. And what this allows us to do is that if we have 100 grams and 50% is sulfur, then that means that we have 50 grams of sulfur. And the same thing with oxygen in this case. We're then going to take these new gram amounts and we're going to find the moles of each. So 2 calculations because we have 2 elements. This goes back to concept A where we're going to be converting to moles using the GFM in this case of sulfur and then of oxygen. When we make that division, we find that we get 1.56 moles of sulfur and 3.125 moles of oxygen. Now, this is their relationship in that compound, but we don't like plugging in decimals for subscripts. So this is a key part. Once you find the moles, you're going to divide each of them by the smallest amount of moles in all the different elements. So sulfur is our smallest at 1.56. I'm going to divide them both by 1.56, and when we do that, we're going to see in this case we arrive at whole numbers, 1 and then 2 oxygen. So this gives us the ratio between sulfur and oxygen. For every 1 sulfur in the compound, we have 2 oxygens, which then means we can simply plug it into their formula or get sulfur dioxide. Now, one thing I will point out, and this will happen in class, is when you get these numbers, if you happen to have one that's 1.5 or 2.5, you would have to multiply all the numbers by 2 in order to get them to be whole numbers, because we wouldn't want to put any 0.5s in our formula. So here's another example. In this one, we're working with an ionic compound. It says, what's the empirical formula of a compound that is 18.7% lithium, 16.3% carbon, and 65.0% oxygen? So again, we're going to assume out of 100 grams. So we take all their percents, put them in grams. We're going to convert them each to moles. So lithium, using carbon's GFM, and using oxygen's GFM. Then our next step is to divide by the smallest amount. As you can see, carbon has the smallest amount, so we're going to divide them each by that amount. So we divide lithium by it to get 2, and oxygen by it to get 3. This then, because they're all whole numbers, becomes our subscripts. So our final answer is Li2CO3, or lithium carbonate. All right, so that's one big piece of this, and we're going to be working with these quite a bit tomorrow because it can be a little bit tricky, but once you kind of nail down the steps, it'll make it a lot easier. Finally, we also can take our empirical formulas and determine the actual molecular formula of a compound. And how we're going to do that is using its empirical formula that's either given or that you just calculated, and a provided molecular formula, GFM. So this is just a little chart to kind of show you the steps, and then we'll do one that's a pretty close example to what you might see on a worksheet or on a test. So here we know, or have been given, our empirical formula and then the GFM of this unknown molecular formula. So the first step is to simply calculate the mass of the empirical formula, which is 88 for this compound. I then need to see how many times bigger the molecular formula is. So if I do 176 divided by 88, I see that the molecular formula's mass is 2 times larger than the empirical. So I'm simply going to multiply all the subscripts of the empirical formula by 2, which means that my final molecular formula is C6H8O6. Same thing with this next one. Find the mass of the empirical formula that's been given. See how many times bigger the molecular formula is. So 45 divided by 15, which gives me 3. That means that my molecular formula is 3 times larger than the empirical. So I'm going to multiply all the subscripts by 3, C3H9. So our final practice, and basically this is how that type of question is going to look. You won't see it in a chart. We have a substance that has an empirical formula of CH and a molecular mass of 78.0 grams per mole. Determine its unknown molecular formula. So we first find the mass of the empirical formula, okay, which again is just CH, so we get 13 grams per mole. We're then going to divide the molecular formula's GFM, which is given to us by that calculated empirical formula's GFM. So we get a 6. That means that my molecular formula is 6 times larger than my empirical formula. So I'm simply then going to multiply the subscripts of our empirical formula by a whole number, which was 6. And since it was just 1 to 1, it now becomes 6 to 6. And that is it. So we'll be working on all these different calculations tomorrow. I would though run through, especially the steps for each, make sure you have that clear, and then we'll apply it in class.